We have come to the end of this short course on mechanics, heat, oscillations and waves, and what I would like to do today is to kind of give an overall picture of all that we have been through, all that we have studied in some detail during this course, and also put matters in perspective and suggest what we should do next and in preparation for a future course. We started by discussing dimensional analysis, scaling relations, order of magnitude estimates for physical quantities. So, I made the points here that we have a certain tool at our disposal called dimensional analysis, which helps us guess the combinations of physical quantities which could appear as answers to questions we ask about physical problems. So, this is a very powerful relationship, this is a very powerful tool, it has its limitations, but as a first order guess or zeroth order guess of what the answer is, it often gives us very wonderful answers, surprisingly powerful answers for questions which appear to be very difficult a priori. Scaling relations is a kind of generalization of dimensional analysis. I did not get too much into it, but the reason I am mentioning it is because you should be aware that these are the tools, this is the starting point and these are the tools with which one analyzes real life problems. Conservation laws was what we looked at next, and I used the vehicle of collision kinematics, two body collisions, elastic collisions, in order to bring home the effective power of the laws or principles such as the conservation of energy, momentum and angular momentum in mechanics. I also took care to point out that the origin of these laws lies deeper. The conservation of energy follows because of time translation invariance. In other words, when a system's behavior in time does not depend on the absolute origin of time, when the laws are independent of time in that sense, then you have the possibility of conservation of energy. Similarly, the fact that space is homogeneous to start with in the absence of fields or forces and so on leads to the fact that you have conservation of momentum under suitable circumstances, and the fact that space, which is 3 dimensional, is isotropic, has empty space has the same properties in all directions, again unless broken by the appearance of a field or a force or something like that, you have then the possibility of angular momentum conservation, and used properly these put a great deal of constraint on the kind of solutions that one can have for physical problems. They also help us in arriving at these solutions, because constants of the motion in general in dynamics mean that every time you find a constant of the motion, you have gone closer to a solution, that much closer to a solution. As I said, I used collision kinematics. We did not put in any dynamics except to say that two balls or two particles collide with each other elastically. We did not say anything about the nature of the contact forces between them, and yet you are able to derive a great deal of kinematic information about the momenta before and after the collision or the energies after the collision using just the conservation principles. Okay. Dynamics, just one point here, recall that in this case where you had two particles colliding with each other and then going off in opposite directions, these or in arbitrary directions, this particular problem involved the knowledge of the two initial momenta, and the calculation of the two final momenta was what was needed to find out what is the final momenta after the collision. But there we discovered that the conservation of energy, momentum was not enough to determine the problem completely. You needed to put in some dynamical information, and I did that by saying, well, let us assume that one of the particles moves off at some given angle beta to the initial direction of the projectile, and then in terms of this beta we were able to derive the other quantities. To find the beta itself, you need to know a little more about the dynamical process here, and that is the process, that is the problem of scattering theory in general, just to complete what I had said earlier. We then looked at Newton's laws of motion, the 3 laws of motion, and I pointed out that it is not as if the first law is a special case of the second, or that the third law can be derived from the second, no such thing. The second law contains dynamical information, it is the basic equation of motion in Newtonian mechanics. The first law essentially tells you what an inertial frame is, and the third law is a relationship which Newton discovered for the first time, namely the force of particle 1 on 2 is minus the force of particle 2 on 1. This leads to the conservation of angular momentum of the system as a whole. On the other hand, today our understanding is that spatial homogeneity leads to the conservation of linear momentum, of the total linear momentum, and that implies Newton's third law as a special case when you restrict yourself to two body forces, two body problems. So much for Newton's laws of motion. In solving these equations of motion, I pointed out carefully the role of initial conditions. In other words, dynamics happens in the space of not only the coordinates of all the objects concerned, but also their initial velocities or momenta. That is an important thing to understand. The equations of motion of Newton are second order equations in the displacements or in the position vectors, and they require two initial conditions, the initial velocity as well as the initial position. So, role of initial conditions is crucial. In fact, the number of initial conditions you need for a dynamical problem tells you the dimensionality of the phase space in which this motion occurs, the dynamics occurs. So, the next thing we did was to introduce the concept of a phase space and then the concept of phase trajectories, pointing out how a huge number of initial conditions, in principle an infinite number of initial conditions on any phase trajectory, could be described by one common trajectory. For instance, if you had a simple harmonic oscillator, the xp plane, in the xp plane the motion in phase space, in this case the phase plane, was essentially on an ellipse, and you could start anywhere on the ellipse and the periodic motion would cover this periodic orbit over and over again. So, that is one way of combining a lot of initial conditions into one description, but the phase space analysis is much more profound than that, and in higher dimensionalities it leads to a great deal of insights into the dynamics itself. So, the idea of phase space and phase trajectories is basic to the understanding of dynamics of all kinds of systems. We also took a brief look at the importance of equilibrium points, both stable and unstable equilibrium points, and these points in some sense are the markers, if you like, around which dynamics takes place, and these are the points which characterize systems, dynamical systems. The idea of equilibrium points and the generalizations, which I have not talked about in this course at all, characterize, if you like, dynamical systems in general. We took a brief excursion to looking at what are called inertial forces. In other words, the forces or pseudo forces that appear when you write Newton's laws in terms of frames of reference which are accelerated. In particular, we looked at a rotating frame of reference with respect to the lab frame, say, and discovered that apparent forces or accelerations, in this case the centrifugal acceleration and the Coriolis acceleration, arose very naturally from the fact that the coordinates themselves, the coordinate axes themselves, were time dependent with respect to an inertial frame of reference and had an acceleration. And the case of rotational motion was particularly revealing because it automatically brought out the existence of a very real effect, the Coriolis effect, as well as the centrifugal force which acts on bodies in rotating frames of reference here. I also mentioned that depending on your frame of reference, the way you look at the weightlessness of an astronaut in a satellite, or our weightlessness, even though we are freely falling in under the gravitational pull of the sun as the earth orbits around the sun, can be understood once one analyzes the problem correctly in any given frame of reference. In the sun's frame of reference, we are in free fall, the earth and everything on it is in free fall, so we do not feel this force directly because we are essentially freely falling under it. From our point of view, we do not feel the sun's gravitational pull because we are the force of gravity due to the sun. The centripetal force is balanced by the centrifugal force which we feel since we are in a rotating frame of reference. So, the same thing can be translated to the case of an astronaut in an artificial satellite around the earth. Next, we looked at the central force problem. In particular, we looked at the Kepler problem, which corresponds to a 1 over r potential, or the inverse square law of gravitational force, for instance, or Coulomb's law, and we discovered that this particular problem has special features which are summarized in Kepler's laws of motion, Kepler's laws of planetary motion, namely that the closed orbits are ellipses with the sun or center of attraction at one focus, that equal areas are covered by the radius vector in equal times in the orbit, which is nothing but a statement of the conservation of angular momentum about the center of force. And Kepler's second law, I pointed out, is applicable to motion in any central force. In particular, it is applicable even to hyperbolic orbits and not necessarily restricted to elliptic orbits. But in general, when you have a central force, there is no torque on the particle which is subject to a central force, and therefore the angular momentum about that center of attraction or repulsion is conserved as a function of time. Okay. We saw that Kepler's third law, which said that the square of the time period is proportional to the cube of the mean distance from the sun, or the mean radius of the orbit, is actually a consequence of the 1 over r squared law of force. And if this 1 over r squared were replaced with some other force law like r to the power n, then you would get a different quote unquote Kepler law, third law, even if you did not have closed orbits. In particular, when you had a harmonic oscillator force, namely the force was proportional to the first power of the displacement, then we discovered that the time period is independent of the amplitude of oscillation, which is a special case of Kepler's third law, if you like, or some law similar to it, and that is a well known fact feature of simple harmonic motion. There was a brief excursion into elasticity of solids and elastic moduli. The key point here was, I pointed out that there are for an isotropic solid there are two independent elastic moduli, and there is a relation which relates the Young's modulus, the bulk modulus and the shear modulus, or the Young's modulus, the bulk modulus and Poisson's ratio, or Young's modulus and the bulk modulus and Poisson's ratio, and so on. So you have two independent elastic moduli, and stability, thermodynamic stability essentially gives you certain constraints, such as the fact that the Poisson ratio must lie between -1 and +½ although for most standard materials like metals it lies around 1/3 or so, but theoretically it cannot be less than -1 and greater than +½ due to thermodynamic stability here. We went on to wave motion, and there I wrote down the basic wave equation, even though it involved some partial derivatives, and then introduced the idea of a wave or phase velocity, group velocity, the superposition of different kinds of waves. Since you have a linear equation, superposition applies, and then we also took a brief look at the Doppler effect. I wrote down without any derivation the formulas concerned. I also wrote down the corresponding formula for the relativistic case of the Doppler effect in the simplest instances. The next topic we looked at was fluid dynamics, which now concerned, if you go back here, we started with the dynamics of individual particles or bodies, and then we went to a continuum. In the case of wave motion, like waves on a string, or waves, sound waves in a medium like air, and then fluid dynamics tells you about the dynamics of these continuous media, in particular a liquid, and we gave a condition for hydrostatic equilibrium, and after that I derived Euler's equation, which is writing down Newton's equation for a fluid element, and we discovered that it was natural to introduce in the time derivative of the velocity the idea of a convective derivative. So basically we ended up saying that the total derivative d over dt was symbolically something like this. When applied to the velocity, and that led to a nonlinearity in the equation of motion. V appeared in quadratic form, and that I pointed out then that leads to a great deal of complications of fluid dynamics. Fluid dynamics also offered to us a natural way in which we could introduce certain concepts of vector calculus which appear everywhere in physics, such as the gradient. When I introduced the gradient of the pressure to discuss hydrostatic equilibrium, for instance, and then the flux of the fluid as the fluid flows. It is actually the most physically transparent example of the flux that we can think of for a vector field. The flux of the velocity of the current, the fluid flow, led to the concept of the divergence of a vector field. So while the gradient told us how to construct a vector field from a scalar function, the divergence tells us how to construct a scalar field from a vector function, from a vector field. And a vector field from another vector field came out when we considered the circulation of a vector field, which also led to the idea of the curl of the vector field, which got related to the vorticity. And if you recall, I pointed out here that the vorticity of a fluid in fluid flow, which is the curl of the fluid velocity, this is the vorticity, this quantity had the physical significance at any point of being twice the local angular velocity of a fluid element sitting on that fluid element and watching how it rotated. So this gave us the idea of local rotational aspect to the fluid flow, and we gave some simple examples of what happens when you have such kind of rotational motion, such as a boat floating down a river, due to the fact that the velocity in the has a transverse gradient, while the velocity moves in the x direction. As a function of the y direction, the transverse direction, you have different velocities. So as you go down, a little raft is rotated, and this differential in the velocity leads to the idea of the curl of the velocity field. Vortices, again, this mechanism by which energy is dissipated in fluids and finally leads to turbulence in fluids, is intimately connected to the idea of turbulence is intimately connected to the idea of vorticity in fluids, a very complex subject. There was something analogous to under suitable cases for steady flow to conservation of energy, which was came out in the form of Bernoulli's principle, which is used very often in practice, provided you have a streamlined flow which is steady. Okay. We went on after that to look at systems with a very large number of degrees of freedom, typically of the order of Avogadro's number degrees of freedom, and then that it became natural for us to introduce some statistical methods, and I pointed out that what we call thermodynamics is really the science of averages. So you do these statistical methods in statistical mechanics and focus on the average values of various physical quantities, which are macroscopic quantities averaged over a very large number of microstates or configurations of the microscopic entities involved, and this led to the laws of thermodynamics. So we identified intensive and extensive thermodynamic variables, and then we wrote down the first two laws, combined them into one particular law in the simplest instance, and focused on the case of a simple fluid, one component fluid. I pointed out that thermodynamic equilibrium or thermal equilibrium is what we assume in the case of thermodynamic systems, that system is in thermodynamic equilibrium, which means that the average values of macroscopic quantities are time independent. So that is what is meant by thermodynamic equilibrium, in contrast to equilibrium in dynamics. This is for microscopic degrees of freedom, individual degrees of freedom, whereas that says something nothing to do with mechanical equilibrium as such. This has to do with the steady value or the time independent value of averages of macroscopic quantities themselves. So in thermal equilibrium, we have the two laws of thermodynamics, and these laws enable us to get a great deal of information about the system based on considerations which really in some sense are a generalization of what I wrote here of scaling relations. I did not explicitly mention it, but the fact that the internal energy of a system is a function of its entropy, the volume and the number of particles, but it is a homogeneous function, and it is a function of each of these extensive variables to degree 1. I did not mention this explicitly, but that is used in thermodynamics in order to derive relations going beyond the laws of thermodynamics. So it is used in conjunction with the laws of thermodynamics to derive very powerful relations between these thermodynamic variables. I used the ideal gas, a classical ideal gas, as a kind of theoretical laboratory to get some feel for the way thermodynamic variables behave and what one can say about these variables. We talked a little bit about the possible kinds of specific heat that you could have in an ideal gas once you subjected it to a class of processes called polytropic processes, of which the isothermal, adiabatic, constant volume and constant pressure cases are all special cases. So we got a kind of general law for the specific heat, general formula for the specific heat for a process in which PV to the power n is a constant, where n ran all the way from 0 to infinity here. And then we moved on to real gases. In other words, we took some cognizance of the fact that the real molecules would actually attract themselves at long distances and also have a certain range of short range repulsion between themselves. And when you took those into account, we had an empirical equation, the van der Waals equation, to describe this gas, but as a bonus we discovered that this equation of state actually describes not only the gas state but also possibly the liquid state of the system. So it allows for, it has got two branches if you like, and it allows for the fact that below a certain temperature called the critical temperature you have the possibility of separation into liquid and gas, and the van der Waals equation helped us understand to some extent how this change of phase occurred. We went on and looked at a little bit at phase diagrams in the TB plane, VT plane, and most important in the PT plane to understand what the phase diagrams, what the phase diagram of a generic simple single component substance looked like, namely the crystalline solid phase, the liquid phase and the gas phase, and we took a look at the properties of the coexistence curves, the significance of the slope of the PT curve, which is the coexistence curve given by the Clausius-Clapeyron equation, which related the slope of these curves, the way the boiling or melting point changed with pressure, it related it to the change in entropy under this transition divided by the change in specific volume. Okay. I also pointed out that the liquid gas coexistence curve ends in a critical point where the liquid loses its distinctive characteristics, such as the existence of a latent heat of evaporation that goes to 0 at the critical point, that the surface tension goes to 0, the meniscus disappears, and the distinction between a gas and liquid is lost. In the case of water, this happens fairly high. It happens at something like 647 Kelvin, and it happens at more than 200 atmospheres pressure, but there exists such a critical point there. Such a point does not exist between the liquid and solid, crystalline solid coexistence curve. It does not end in a critical point. It cannot, because if it did, you would be able to continuously go from the very symmetric phase that the liquid is to the much reduced symmetry phase of a crystalline solid, a periodic array, and this is not physically possible. So in this case we can make a general statement based on symmetry considerations that there can be no critical point in such a coexistence curve, whereas in the gas liquid case there is such a critical point. Things always end in a critical point. I finally mentioned that the critical point, understanding that, requires you to go far beyond thermodynamics per se. It is in fact a point where the normal thermodynamics fails for certain technical reasons, and you need to use sophisticated statistical mechanical techniques to go beyond it. Going beyond that, we have a lot of applications in condensed matter physics which are properly understood only with the help of statistical mechanics, which is a crucial subject which you would at some stage undertake, whose study you would certainly undertake at some stage. What is left now in the next course hopefully would be the rest of the curriculum, the standard curriculum in basic physics, which would comprise things like electricity and magnetism and optics and a little bit of modern developments in physics. Modern is really should be taken with a little advisement, because modern, well, it is more than 100 years old. Quantum mechanics is almost 100 years old. Certainly the idea of the quantum is now more than 100 years old, 110 years old. So it is really not all that modern, but it is really part of mainstream physics now, and that is what we now look forward to studying.